Welcome to the OrionX Download. This is a podcast where we discuss big ideas and big trends in high technology. Hello and welcome to the OrionX Download. I'm Dan Olds, joined by Shaheen Khan and Steve Perrineau from OrionX. And we have a very special guest today, don't we, Shaheen?
We sure do.
Would you like to introduce our guest?
Well, one of the things that we are focused on at OrionX is the intersection of these megatrends that are out there. And two of the hotter ones, they're all hot, but two of the hotter ones are quantum computing and artificial intelligence. And at a conference I was attending a couple of months ago, I ran into a gentleman who is exactly at that intersection and perhaps more. So we have the pleasure of having Max Henderson, who works at Rigetti, the quantum computing leader, and has graciously agreed to join us. How are you, Max?
I'm doing excellent. Thanks for having me today.
Do you want to tell us a little bit about your background and how you got into quantum computing?
Yeah, absolutely. So I got my PhD in physics from Drexel University, and I was studying essentially biophysical neural networks. So trying to understand computationally how the brain ages and how that might affect neural performance. It turns out modeling the brain is quite difficult, and machine learning models ended up being sort of a natural evolution for me as a more abstracted, simplified model of the brain. So my physics PhD kind of naturally led me in the machine learning direction. At the same time, I might be the world record holder for the longest intern at Lockheed Martin. I think I did something like 6 summers of internships between undergraduate and grad school.
That's impressive. They wanted you back for more.
They must have liked me a little bit. And I was debating not actually doing that in grad school, which can get quite hectic, but that just so happened to be the year that Lockheed Martin purchased the first commercially available quantum computer made by D-Wave at the time. And I was one of the people that got access to that back in 2011. So that was my first foray into quantum computing.
Oh, awesome.
Yeah. And from there, it's naturally evolved and has pushed me between my PhD work and the access to this quantum technology through industry. It naturally pushed me into quantum machine learning, which is really trying to figure out how to use these interesting devices for machine learning applications. So it was
Awesome.
kind of an organic process there. I guess the last bit, I worked briefly for JP Morgan as a data scientist after leaving Lockheed in New York City, which partially due to personal reasons, my wife had been assigned medical residency there in the city. That's when I joined QBranch, which was a quantum algorithms and data science software company. And we eventually were acquired by Rigetti last year. So now I'm part of Rigetti on the applications team there.
Awesome. What a great background. So we can probably talk to you about blockchain and cryptocurrencies too at some point.
Oh, yeah.
Yet another trend that we track. So is there anybody in quantum computing that does not have a PhD in something?
That's a great question. This is an interesting field where it's obviously got its toes in both academia as well as industry. Traditionally, most of the people in quantum computing, I would say, do have PhD backgrounds, but it's becoming less of a requirement, particularly as the field of quantum computing moves out of the lab and more into practical applications. So as the overall technology has evolved, you need more than just hardware level physicists and complexity theorists. You also need quantum engineers, people that are able to write really good software, and some people that are just very skilled at a particular subject matter and can offer their expertise for shaping a quantum algorithm. So I think previously, yes, it was probably almost exclusively a PhD field, but as it's grown, just like I think a lot of technologies that mature, you need so many different types of skill sets and people that there's a lot of open job opportunities at more intermediate and intern type levels now.
Right.
That's good to hear.
Yeah, absolutely. I think it's a sign of a healthy, growing industry.
Yes.
Sort of at a high level.
So where is Rigetti at today?
I work at Rigetti, and although I want to make it clear, my thoughts definitely here are my own, so I'm not speaking like a public spokesperson for Rigetti.
Of course.
But yeah, so Rigetti is one of the largest pure quantum companies in the world. There are some large companies such as IBM and Google that have parts of the business devoted to quantum computing. But Rigetti is exclusively a quantum computing company. And the focus for them is to build quantum hardware, particularly that shows what we'd call quantum advantage over classical devices. Quantum advantage in the sense means that we have shown either increased accuracy or performance, or have cut down on a total runtime, or have done something that requires far less computational energy or some other kind of cost than is possible with a similar classical algorithm. Right now, Rigetti as a company has been able to produce their own fabrication unit for making quantum processing units or QPUs from scratch. And we also have an applications team that is working on figuring out the best ways to leverage that hardware technology to solve real problems, and a lot of software folks in the middle that are trying to optimize the whole stack. So we're, I believe, a bit over 150 people now, and continue to try to iteratively improve on the hardware level performance, as well as the types of applications that would be most performant given the hardware restrictions we have.
Max, this is Stephen Perrineau. How is it that Rigetti got into the AI related and deep learning related activities, and how did they choose that this was appropriate for investigation with quantum computing techniques, and what is the scope and size of the team that are working on AI related topics?
Stepping back quickly, just to make sure, we've been talking a lot about quantum computers, which is not the only technology that uses quantum mechanical systems for technological purposes. There is quite a wide variety of technology that use quantum mechanical systems for some purpose. We have interesting quantum communication systems that are trying to transport information in a more efficient or resilient manner. We have a field called quantum sensing, which is where you would use quantum mechanical systems to try to improve on measurements that are made using classical sensors. Rigetti's focused on specifically quantum computers, which are, as the name suggests, quantum systems that can perform some type of computation, just like a classical computer. And given that we are in this era of NISQ, which is NISQ, you might have heard of, stands for noisy, which means error prone, intermediate scale, which means small quantum systems. The machine learning application is one of three main target areas that seems really viable for near-term quantum computers. The three most prominent application areas for these, again, small kind of noisy devices is modeling physical or chemical systems. The second is solving optimization problems. And the third is machine learning in general. That's maybe at a high level an answer to how we've focused in on a machine learning focus, and more particularly for why machine learning seems like a nice fit for, again, these kind of small, noisy quantum systems.
Mhm.
There's, I suppose, a two-part answer there. The first is that I can kind of take off my quantum hat for a second and put on my data scientist hat. A lot of problems within data science and machine learning, you're dealing with probabilistic models, and you probably have lots of noisy, messy data that you're feeding into them. And these models probably have to make inferences about correlations or relationships within your data that have effects on each other that can be kind of hard to model classically. This is like actually a really good structural fit for quantum devices that we're making today, which are sort of by necessity probabilistic, as are all quantum systems. You have probably heard about superposition, this idea that quantum bits or qubits are either in a 0 or 1 state potentially before you measure them. So they're kind of these naturally probabilistic units that you're encoding with. And when you start to create a quantum circuit, you entangle these quantum bits together. So you're naturally modeling a correlated system. And finally, as I was mentioning, these near-term devices tend to be a bit noisy and error prone. So you're naturally also generalizing models that you'd be learning on these quantum devices. So you'd be preventing things like overfitting just by, again, the structure of the hardware itself and how it functions. I suppose the second and perhaps even more pressing reason why machine learning is interesting is that we already know that machine learning at scale has a lot of challenging problems in it. And some models are just not tractable at scale. Other models can require quite long training times and a lot of computational energy to extract the right kind of features for some modeling purpose. And we know from a theoretical perspective, certain types of calculations, quantum computers can just do potentially exponentially more efficiently than classical computers. The motivation here is to find sub-processes within a broader machine learning pipeline where the power of quantum computers can somehow augment or improve overall performance or training time or the distribution of types of feasible forecasts or something like that. This is why the field of quantum has converged on machine learning as a use case. It just has a good natural fit, and it's one of the three main areas for near-term quantum computers. And the second, again, is there's a lot of opportunity to potentially find sub-processes within a broader machine learning pipeline where the potential power of these quantum circuits might be leveraged in a way that you can't do efficiently on a classical device.
Right. When we do machine learning and AI on quantum computing, is it just reformulating that problem in terms of an optimization problem, and then we just do optimization, or is it a net new category?
I would say, in general, doing machine learning on quantum systems is almost like a completely new lens of solving machine learning problems. A quantum computer just works radically different than a classical computer. So the problems that you'd solve, you almost have to change how you think about the algorithm itself. I mentioned before, I first started getting to use quantum computers back in 2011. And there was almost a period where my brain had to restructure to start thinking about problems in a quantum way, because every quantum computer basically has their own kind of mathematical framework that underlies how the device works. And they're all sort of dissimilar to a typical classical algorithm. So there are parts of a classical algorithm that might fit onto a particular quantum computational model, but it tends to be, at least in my experience, something that you need to develop a little bit of expertise or intuition for how they might fit one onto the other. And some of these quantum algorithms are almost from scratch. They're truly a novel approach or algorithm to solving a particular problem within machine learning, but where there might just not be an immediate classical comparison, or one that's very different than the comparative classical model.
So, as you go from the traditional way of doing machine learning and deep learning to quantum, you do have to rethink it, that it's just a different style. But is part of that rethinking reformulating the problem in terms of optimization, or is it rethinking in terms of wherever it leads you?
So there is, I suppose, a reformulation between machine learning problems to take a form that might look a bit more like an optimization problem. But I suppose this is where, from my perspective, there can often be a bit of a blurry line between optimization and machine learning in general. Like there's quite a large overlap in some sense for those two fields. For instance, we know that there are particular models within machine learning that involve training, which can take the form of solving a system of linear equations, which is sort of an optimization problem.
Yes.
But it's also for a machine learning type use case, potentially for like predicting an output on a new data point. One of the algorithms actually ran on a Rigetti device is something called a variational quantum linear solver, specifically for solving systems of linear equations potentially more efficiently than you can do with other classical solvers. And that might be for an end use case, which is purely for optimization. And it could also be part of a machine learning model that requires, again, some linear system being solved. So definitely there can be parts of the machine learning models where you reformulate it into an optimization kind of problem to solve on the quantum computer. But it can also be the case that the quantum computer is being used as a device which can be thought of as a sampler. So there's a large field of graph-based models which are trying to essentially draw fair samples from a very complicated distribution.
I see.
And quantum computers are sometimes used as these sampling devices. There's also typically an optimization problem within that sampling that's just being done by the quantum mechanical systems natively. But yeah, there's definitely always sort of a connection between optimization and machine learning classically and quantumly, I suppose.
I think at some level you can reformulate anything to be an optimization problem. But then that may not be the most efficient way of solving it. It turns out you're saying that at least in part that's a component, but there are other aspects to it too.
Maybe another example would be good here. This will be coming out in a peer-reviewed journal very soon, but it's on the archive. We published a paper called the Convolutional Neural Network, which is a clumsy portmanteau I still admit I'm quite proud of. But it's a quantum version of a convolutional neural network. And the elevator pitch for why you would even think about using a quantum computer for that purpose is the way a CNN works, a convolutional neural network, is by basically being a hierarchical series of feature extractors. And as you go up the stack, you're hoping to have more and more complex features that align with some predictive outcome. The very prototypical example is you have some image data set, and the first layer of feature extraction, you're hoping to get lines at different angles. And then a layer on top of that, you might start combining those lines to extract shapes of different types. And then those shapes get more complicated the further up the stack you go until you have neurons which are identifying very strongly with particular complex nonlinear features in your original data set. The quantum version of this is doing something similar, but instead of processing this data through these normal matrix multiplications, we are actually processing them through quantum circuits. And the reason we think this could be useful is that, again, we know certain quantum circuits on certain types of input data are just exponentially more efficient than you could do classically. So hypothetically, if you could find a series of quantum transformations that are extracting features which are both, one, useful from a modeling perspective, and two, classically hard to simulate, then you would have a quantum algorithm which is doing something very useful and seemingly only possible by using a quantum device. This process is a feature extraction process within a machine learning pipeline. And on top of this, there would still be an optimization happening where you ultimately have a loss function and you're trying to update kind of the parameters within your whole network. So there's always going to be this relationship back within machine learning to some kind of optimization. For CNNs, it's trying to reduce some overall training loss function. But within part of that, some of the processing could be given a boost using a quantum computer.
That's excellent. Love to get the link to the archive.
Yeah, it's definitely.
One other question, really the development environment. Can you speak to how much easier it's got to program these things and how much more distance is left?
So this is often a bit of a joke that this field is sort of like starting over in the 1950s or 40s or something, where I never in my life imagined that I would have to be programming things on the bit level, like essentially telling individual parts of a machine the particular parameters I want them to run.
Wow.
But that's kind of where we are in the quantum world right now. This is still very early days. I'll give an example here. Rigetti makes universal quantum computing circuits, and these have a very rigid topology. What that means is that when you fabricate a chip, each qubit has an individual qubit ID and a particular set of other qubits that they're connected to. Right now, if I'm running an algorithm which needs to, for instance, use a fully connected graph, if my quantum computer is not fully connected, I can't run that directly. I would actually have to find some way of remapping that problem so that it fits natively onto my hardware device.
Right.
There have been software tools for making things much easier. And the fact that I can program in Python and still talk to a quantum computer, I think speaks to how much the development environment has evolved. However, we're still at that era where you do need to have some level of awareness of how the actual physical device itself is built and how it performs, and some of that nitty-gritty under the hood type information that we'd hope you would not need to be quite as aware of 10 years down the line as a software developer or as a quant at a bank that still wants to use a quantum algorithm. But right now, the software has been growing by leaps and bounds, and there are constant improvements that are being put out publicly on GitHub and of course developed internally within the different companies, but it's still relatively early days. And this is partially why it can sometimes be a bit challenging getting in if you have absolutely no background in quantum physics or mathematics in any rigorous way.
Right. So you still need some level of a specialization. But you're right. I think it's a good analogy that it's just a little behind traditional computing. But as I was saying, traditional computing there are things it could do way better that maybe you can fix in the process.
Is this somewhat analogous to how the very first computers were put together, working at a bit level?
Yeah, absolutely. I think that's exactly right. We are thinking about things at the qubit level right now. And down the road, I think kind of the marvelous thing is that we're at least able to take advantage of some of the really sophisticated classical programming languages that have been developed over the last few decades on classical computers. So I don't have to learn necessarily some new specific quantum programming language. I just have to be aware of, yes, what is happening at that quantum bit level when I'm making algorithms that are going to ultimately run on actual quantum hardware. I don't need to use a punch card to do it. I can still use my favorite Python packages and all that good stuff. That seems like a big advantage right now.
Right. When you look at quantum computing landscape, there's clearly the gate model and the annealing model, and then there are other novel paths. It seems like nature gives you several different ways of creating entanglements and superposition and do so in a way that you might control.
Mm-hmm.
Do you see it settling down towards one or two or three different paths, or are we still kind of experimenting with different scientific bases to do these things? And somebody may still come up with chemical solution that might do this,
Mm-hmm.
to make up an example.
You pointed out an absolute truth, which is that we, in this era of quantum computing, don't just have different physical qubits that are making the devices, because we also have that challenge too, right? You might just be talking about
Mhm.
a universal quantum circuit based computational model. And there's lots of different types of fundamental physical bits that people still argue about which kind of should we be using ion traps or superconducting wires, even more exotic material like topological qubits. So that's its own kind of debate in the community that's playing out in real time, essentially, as people develop their own solutions. But like you mentioned, even beyond that, there's actually completely different quantum computing models that people are experimenting with. So the quantum annealers built by D-Wave are a completely different sort of mathematical model, not completely different, but quite different than the universal quantum circuit-based models developed by like a Google or a Rigetti. And those in turn are all different from some of the more exotic models, for instance, a Gaussian boson sampler, which is developed by Xanadu, and they're computers based on photonics. So yes, there's this really interesting place right now where you have very different material that is not clear which one's the best for these different frameworks, and the frameworks themselves are quite different for how to do computation. I would say I feel quite strongly resonant with the statement you made about nature kind of potentially having different good solutions based off of the different types of frameworks. So I kind of think that down the line, we are going to keep improving iteratively on all of the different types of models. And eventually, certain problems might just be better ran on particular quantum hardware backends, based again off of the fundamental advantages those devices have. However, you can never discount the fact that if all of a sudden there seems to be a very highly useful application that's running incredibly well on one particular framework, that could kind of dominate the conversation and the development for some amount of time before maybe some of the others catch up. So it's a pretty, I would say, volatile space potentially at the moment. But the physicist in me would say that each of the underlying computers have a different structure that has advantages and disadvantages. And I think those will ultimately translate into applications that map well onto the advantageous qualities of the underlying hardware.
Yeah, I tend to agree. I think that we are going to find problem spaces that naturally lend themselves to a particular style. And hopefully those represent a big enough market to make a go of a subsegment of the quantum computing market.
Mm-hmm.
So along those lines, what do you see on the horizon as it relates to AI or quantum computing? Or we didn't talk about cryptography, but we can mention that as well. What's your projection for the next couple of few years?
There's a couple main models and I suppose algorithmic families people are quite keen on for quantum machine learning or QML. As I mentioned before, there's some pretty interesting sampling applications. Models such as the quantum Boltzmann machine or the quantum circuit Born model are two quantum algorithms which can be used to produce synthetic data and in turn be useful for forecasting things. There are quantum versions of generative adversarial networks which have been looked into for denoising images or increasing the resolution of data. Quite a lot of classification problems, which might be useful to look at through the lens of quantum computing. I mentioned the convolutional neural network as one of these examples, but there's quite a lot of quantum algorithms where the quantum circuit is essentially posed as either part of or the entirety of a neural network in some sense for classification or predictive purposes. And as I also mentioned, there's some interesting applications for solving various types of equations, such as systems of linear equations using quantum devices as well. All of these applications and use cases are being explored in the research community and also being looked at for industry as well. I think that the challenges right now are figuring out how to find particular classical data sets that there is an advantage using a quantum computer on, because that can be a little elusive.
Right.
And also really clarifying the expected benefits of using that quantum algorithm. This is maybe one of the fundamental challenges in the quantum machine learning world, is that they face some, I guess, similar challenges to machine learning, wherein because you have arbitrary data sets and it's very difficult to make strong theoretical claims about some of those things, it's hard to know exactly what to expect a priori, I think sometimes, especially with these NISQ algorithms, which are often heuristics and variational by design. So right now, that's one of the challenges of the field, is honing in on the features both of the classical data sets and models and of how to use the quantum circuits or systems to get the biggest bang for your buck, and also figure out what doesn't work. There's been a few quantum machine learning use cases which have actually been de-quantized, which is a fancy way of saying a classical algorithm was actually come up with after the quantum one that showed an advantage or equal performance to the original quantum algorithm.
Yes.
So Ewan Tang sort of famously published this paper, actually as a high schooler, that analyzed a quantum algorithm for basically doing product recommendation. So this quantum product recommendation algorithm was essentially a quantum machine learning algorithm that gave a scaling advantage over any currently known classical product recommendation algorithm. And her research basically took a quantum inspired approach and looked at that quantum algorithm and came up with a classically implementable version that actually scaled even better than the original quantum algorithm itself.
Right.
This is also one of the challenges of QML and everything within quantum computing, is the second you think you have something that might be giving you an advantage, the classical computing world might actually come up with their own clever idea built on top of that pushes the boundary even further. The jury's still out for exactly the quantum machine learning model that would show some kind of performance advantage right now.
Right.
But we're exploring how to better choose things on both the classical and the quantum side to try to get that advantage.
I think that's a great point, that quantum thinking actually has its own benefits, even if you're not going to use it for quantum computing.
So, well, I'll just put you on the spot a little bit, Max. What is your own personal timeline or outlook for quantum supremacy in the machine learning space?
I would say that for a quantum machine application to show advantage, I still am very optimistic for. But I think the challenge is going to be that it is not going to be what people would be expecting. I think oftentimes when people talk about a benefit of a quantum computing system, the first thing they think is Shor's algorithm, which is the very famous quantum algorithm that could be quite dangerous for cryptography. And that algorithm has an exponential advantage over any known classical approach. I don't think there's going to be any exponential benefit in the QML world within the next 5 or 10 years. But I think what we will see is iterative processes as we, again, really try to perfect how to use the device and the outer loop classical algorithm as efficiently as possible. And I think we might be able to expect something like a polynomial advantage within the next 5 or 10 years, I think is quite possible. But within the next year or 2 or 3, that also could happen. It just is hard to predict. And even if it was observed, it would probably take additional time to rigorously test and believe.
Right. Well, excellent.
Very good. This has been amazing. Thank you so much for the glimpse into what's going on with quantum and what you guys are doing, Max. We really appreciate it.
Oh, thank you so much. It was a pleasure to be on the show.
Yeah, really looking forward to keeping in touch. And we're going to look up that article that you mentioned and others that you might send our way. So good job doing all the great work that you guys do. Such an exciting area. And we are going to come back and separately with you and probe all those other areas that you also have expertise in.
Well, that sounds great. Always keen to talk on quantum and machine learning. So happy to answer any other questions. And it was a pleasure chatting with you all today.
Thank you very much. And thank all of you out there for listening to this edition of the OrionX Download. We will talk to you soon.